Okay, good morning, everybody. I think I have to silence this. So it seems it's a tough morning. So many people missing today. Maybe it's the Pepero morning day. So as usual, a little bit delayed with your assignments. I will try to return sometime next week. And maybe for this latest assignment, I will have no time to give feedback, so you will have only the grade, right? Because until Wednesday, we are totally full-time with accreditation, and I don't want to delay it too much. Today, we will continue with the envelope, but we have many pending explanations, so I will do it now. I think it was quiz 5, not quiz 6, but probably that's not very important. So it was quiz 5, right? So we had a lot of absences. 7 people missing one class is quite unusual. But I wonder if we can do even more absences there. The average was quite low, just 6 points. And it was probably the worst quiz we had. So we had a lot of weight in the lower part and quite a lot of the failing. For the first time, I think 0 points, which is hard, right? Because even by coincidence, just by chance, you should have some probability to have something right. But still, we have the usual number. So many people had 10 points. So I guess it was not that the test was difficult. It was that for some reason things are a bit messed up this semester. And many people didn't go into the lectures, didn't study, and so on. So I don't think we needed to explain the questions because they were just straight from the lecture. There's not mystery. I went to YouTube, and the lecture of waterproofing was viewed by only 20 people. And nobody saw the complete lecture, right? Plastic was online, and there was not any kind of comment or question about it, which is okay. Maybe it was clear enough. And for the sustainability in timber, the access to the lecture was even minor. So, yeah, I think each lecture is important. So I would suggest that you find some time to see the video uninterrupted, to go to the handout, and to ask if you don't understand things, right? So next week, next Tuesday, we'll have a quiz 6, which will be the same contents, right? Sustainability in timber, plastics, waterproofing, fireproofing, so on, and the introduction to envelope. And my idea is to take the best score of quiz 5 or 6. So you have an opportunity to get better. Unless that may complicate, maybe both the scores, because if you do very well both, they might benefit your final score. So just to benefit those who studied a bit more, right? So please find some time. The semester is almost over. It's not almost over. We have still 6 weeks, including this. So there's a considerable part of the semester. And in general, the group is doing very well. So do not get tired too soon. Activities, as I said, The online lectures were not so successful, so there's not many comments. Of course, they didn't have activities, but still, there is something interesting. We had in the introduction to the envelope some comment about thermal mass, and I commented that HANOC has this kind of unique feature of having tectonics, but also having thermal mass. And quite a few people said thermal mass is not necessary in HANOC. And well, I'm a bit confused because, of course, I'm not a specialist, but you have quite, this is traditional HANOC. This is the Ondol base, which is a series of conductions, right? Going to the chimney at some point, over which the floor is built. And those brick or stone walls accumulate a huge amount of heat, right? And that's thermal mass, right? That's part of the Ondol part. So the Ondol, traditional Ondol is a heat accumulation system. Then the roof in HANOC, in temples, traditional Korean roof is really heavy, right? It has a big layer of mud, right, of clay, not only for the shape, but obviously given that mass that will benefit in this very extreme climate. And of course, in southern facades and sometimes in others, we have this kind of light enclosure you can totally open, but there is always kind of massive walls, at least in the borders, right? So yeah, I'm not sure about this. Of course, you can build HANOC very light, but that is not HANOC anymore. It is Japanese construction. We commented on Park Kin-leong, architect, last week. He has a lot of interesting articles you can access. This is very lucky. And he studied in, well, what we call now Seoul University, right? It was like Kyungsong Daehakyo, Kyungsong, whatever. And he wrote that he was mad at Japanese architecture. It's just a paper, it has no mass. How can that be a house, right? It's like it's against the genetics of the Korean feeling of architecture. So I think, yeah, we should be a bit more open and really see the reality of things. Other things about this simple detail, we copied in class, and you did well. We have very short time. I gave just the outline to make things easier. So there's one part that many people did wrong, right? If you see, we have just the concrete wall with this waterproofing, right, before the masonry, and many people put it in the wrong place, letting some kind of weird, different kind of structure. And it is surprising because you only need to look. Remember that this course has, for some reason, the SPC for graphic expression and for visual expression. So drawing is not just doing something nice on paper, it's about looking, understanding, and applying the reality, not something which is wrong. We have a tendency to look and to draw from reality. Even copying things, which is easier, takes some kind of concentration. You need to make a memory effort, look and check what you do. And since this is hard, we naturally rely on our memory, right? And we do what we know, and then we do not do things well. So there were more things, but I think it was so general, I was a bit surprised. So please be careful when you copy, at least copy right. And of course, we didn't have much time, but only putting the numbers is not enough. You have to put the keywords and know what is what, right? You don't need to put a full paragraph, but you may have noticed one of the most common notes I put in your assignments is draw more, write less, right? But still you have to write something. Yeah, we need to complement with at least some basic keywords and things like that. So about questions and answers, we have very few. I probably will upload questions and answers from plastics from previous years, so you may want to look at it. But for instance, we got here's some questions. One was about this I think you can see it, this kind of a texture in the exposed concrete walls in which you have this kind of funny circular openings. This is due to the way of construction. When you have the forms, which is usually some kind of a wooden board, there's many versions of that. In a tall wall, when you pour the concrete, there's a lot of pressure, right? So supporting that's difficult. And one way of doing it is with a steel cable with some tensors, right? To do that, you need to make a small pipe. And that's enough to have this very simple without needing a huge scaffolding outside. Then when it is finished, you just fill the holes with a non-retraction mortar. Okay, let me try again. Okay. So that's the why of that texture. Mozzarella. Okay, if it keeps doing like that, I might return to the computer, but then I cannot mark on the screen, which is a bit annoying. Okay, let's see if it works. Just behave for 1 more hour. So there was a couple of questions about cracks in concrete. We spoke about this kind of put-in joints in buildings. There's no way to make, or very difficult way to make a totally continuous concrete with any kind of joint. And that was in the context of the Ernesto de Meuron building, right? Then there was a question about the possibility of grooves in facades, right, in walls. And of course, I will explain a bit more of this. And of course, you can make grooves in walls, right? Only the engineers have to decide how much, how deep, how it will affect the structure. But of course, we do all the time. So this is the backside of the Mimesis Museum. When you visit buildings, you have to see all the sides, right? And very few people go around and see the past, which is interesting because those things we have also to solve, and they are kind of counterpoint to the very sinuous facade. I commented Álvaro Siza is crazy about jointless. He likes to have things continuous, and some of his buildings are famous because having huge concrete area with that kind of joint. In this case, there's kind of very subtle division of floor by floor, very subtle. I think this was just because of construction convenience. This is just the shades of the earthing of the how do I say, the lightning protection, right? But you will see that this is Álvaro Siza with a good client, right? Probably Ernesto de Meuron had to offer more technique and more money. But even here, I don't know if you see the joints of the different pourings, right? So concrete is poured floor by floor or every 2 floors, and those joints appear. No matter how careful you are, this was the joint of the fresh concrete with the old concrete. And then, even though they are careful, you can see cracks appearing in some places, right? So concrete eventually cracks. And this is the point. This is very hard to avoid because of the nature of the material. If you go to the mountains, Puckansan is a pure granite stone, and it cracks with time because it contracts, expands, and after one time things just decompose, right? So this building is amazing, right? The texture is very clever because this strong texture will probably mask any kind of small cracks, right? But there is that I saw, I went to the place, and this is just the small difference between the forms. I didn't see any groove. So it will be interesting to see how this building looks in 10, 20 years, right? How do you achieve this? Well, it's not easy. And Esteban de Meron are famous for the many of having like a continuous concrete without kind of other lines which interrupt things, right? So something you will see often is like having small bits of steel, right? Distributed in a mass. So that creates a lot of protection against those cracks. But you will see them in facade and they will oxidize. Sometimes additional very small mesh of steel near the border, which is so difficult because pouring concrete is very aggressive. So if it touches again the form, it will deform. So I'm not sure what they did here, right? I don't have the details. But if we go to the interiors, right? This is IKEA store, which is not square meters, but hectares of concrete floors. This is actually, they are very nicely done, but you see they have a joints, the typical joints of a brass, but you can see those small bits of steel, right, which are mixed in the mass, and that prevents the cracks quite nicely, right? I think it's the only time I saw this. I studied in school, never did it, and so that's the first time I saw it. But even there, you see that eventually you have cracks, right? It was perfect for a few years, and I was amazed. But this building may be already 15, 20 years old, maybe 20, and it cracks. So that's the thing with concrete. Well, there were questions. I don't need to comment. So how much thick can be a wall? Well, as thick as you want. You are the architect, you are the boss, you design it, right? We saw that a brick building, Monadnock building, we had almost 2 meter thick walls of brick, right? The problem with the thickness is that you lose a space, and the space is expensive, right? And nowadays we can make like construction. The comment of thickness is that we need a huge amount of insulation to have those zero energy buildings, right? And that's something which we didn't solve perfectly yet. And of course, if it is a massive construction, the weight has a lot of influence. This is why skyscrapers need to do things as light, as thin as possible. And I think it's about the process of cladding, right? You have glass and cladding. If you are using mortar to fix the cladding, better glass is at the end because the mortar can damage the glass. If you are fixing mechanically, that's okay. You can do everything at the same time. And that said, we're going to the windows. So I was debating if doing windows and curtain walls together, but I separated because he had this kind of initial explanations, which took some time. And I reviewed the time we have left, which is not much, which means we have to concentrate and be careful, but it's also good because the end is getting nearer. So nice to see you. Good morning. So we will have today windows. On Tuesday, we'll have curtain walls. With that quiz, please study. Of course, the questions will be different, I think, right? And then we'll have like 2 sessions just with case studies of envelope, windows, curtain walls. Here I gave some case studies at the end, which I will not explain. We'll do in the previous session. And then we'll go into flat roofs, sloped roofs, and 1 session of detailing. And then we'll just have the time to finish the rest of the lectures. Okay. In the photo, this is one of the most amazing, I think, the record of broken windows. This is Detroit Central Station, which has been abandoned for many years. And actually, it was dangerous. I took the photo. This is as near as you could get if you want to return alive home. This has been renewed recently, right? But this building has been abandoned for maybe 15 years, 20 years. which is some of the weird things that happen in those American cities. Okay, we have some comments. Midterm exam, I didn't forget. Midterm exam, we had 50 people, 3 were absent. So the 3 students, I assume they already gave up. It's a pity. Because, okay, sometimes you are overwhelmed with courses and so on, but this is one annoying course. So if you can pass it, you have it done as soon as possible. The average was 67% of the score, which is rather low, right? Still, 3 students have over 90%, right? Best 4 were 2 boys and 2 girls, so that means some balance, right? Congratulations to those who had over 90 anyhow. Majority was actually over the average, right? So that would be the average in terms of like a B plus over, right? And we had 9 students on the fail level, which doesn't mean you fail the semester. That means that your knowledge is very poor and you should study more if you want to have at least the basics. Because of that, as I said in the post, put in the Blackboard, I raised a little bit. So I put in the highest was 93. So I put it 100, right? And I did the proportion to everybody. So in that case, only 3 students were in the F. And still they are in the possibility of passing the course. So 11 questions out of 60 were failed by more than half the class. So they qualify like slightly hard and difficult. But I was surprised by the questions which are most difficult. And by far, the most failed. That means only 20% got it right. That means a few people knew, and maybe a few of them got it right by chance, because you have 20% chances to guess it, right? Just this one, which is just an elaboration of the concept of cold stretching, right? And usually about half the class has it wrong, but 80%, I think, is the first time. And the question was not so difficult. We had explanations, we have questions and answers. You know what is this, right? This is a stress strain graph of steel simplified. We know that if we apply stress, the steel will stretch linearly, proportionally, at a given point, which is the elastic limit, right? We say it is not totally precise, but okay, we call it the elastic limit. It will not be linear anymore. It is the plastic period. So if at the point A we stop stressing, the steel will go back to the relaxed period, but will have a permanent deformation. But that return is linear. That means the elastic limit becomes higher. It's not too much complex engineering, and it was repeated. Of course, I didn't mention cold stretching and anything like that. I suppose your human intelligence are able to relate things, right? And this was exactly the same graph we used in class, which makes these things a bit surprising. So I didn't plan to explain, but I explained again. This is the last time. Again, if you don't get it right, you can live with it. But it's a bit embarrassing that very basic science is a mystery. And a shame for me not to be able to have explained it clearly to you. The second and seventh, so it's a question with 2 points, were actually planned as difficult questions, were the ones in which we have this kind of logs, and we had 2 questions about them, which kind of timber it is and where we'll use it. So the point is, this is the same log in 2 different positions, right? And we said it's a very dark part and more expanded. So that is typical of a softwood, right? This is what we call the reaction wood, right? And there's many ways to this. Could have been the same quality of timber. If it's the same quality of timber, it will be the difference between belly and backwood we saw in class of the trees, right? And then the reaction will be different. So this area is reaction wood of softwoods, which is very strong in compression. Then we have the decision of what to do in this graph, right? So in a beam, we have the compression on the top. In a cantilever, we have the compression on the bottom. And then in columns, we'll have mostly the balanced element. This is kind of a just academic question. I know that in general, people try to avoid reaction wood, but I have seen this used. So there's a possibility. So some students said, see everywhere. That was not the intention of the exam, but actually that's a reasonable thing to do. So I gave that also correct. Okay. Those who say see everywhere is correct, but the idea was to make you think about the different positions of timber, how it affects, and the kind of wood we are using. Third, 67%. This applies like a typical hard question, not extremely difficult. It was, again, surprising. This is not any mystery. We're speaking of the long spans, right? And we had proportions for long spans, medium spans, small spans. So it would be like a long, medium, small spans around here, right? Again, this is something you could have taken note. It is very similar in timber, in concrete, in steel. The difference is very small. This is 3 ranges of spans, right? I think it's the first time so many fails in this kind of question. So, yes, please remember that this is just for having a basic proportion in design work. You have to calculate, of course, and things can change a lot. But it is embarrassing. You make still projects with a section of floors which are like 5 centimeters thick, right? Which cannot hold at all. In the same tie break is this one, which is about steel lecture, right? This is a knot in truss, and it was very clearly said that it's calculated through the equilibrium of forces, right? That means all forces have to converge in one point. Here, the forces are not converging in one point, which makes this wrong, whatever, right? All the possibilities are just to confuse those who don't know what we're speaking about, right? Somebody even tried to make a calculation of this, which was not the point. So when you have a small difference between the intersections between the straight lines, you create a moment. And that moment is not calculated. So in this plate is a stress which is not controlled at all. And many of the catastrophes we have in structures come from overlooking this small detail. Okay. So please go back to the lecture. It was explained, it was repeated with examples. This is again one interestingly failed by many people. This was one of the easy questions, right? And of course, glass we can recycle perfectly. It's very simple material. It's very easy to recycle it. You can mix with other materials and do new glass. There's not any limitation in glass recycling. In the same point was timber. By the way, I realized I didn't share the photos of the workshop and nobody asked for it. That would have helped, right? The fail here was about not the cuts. Most people understood tangential and transversal or horizontal. This was very clear, so that was not difficult. It was the hardwood and the softwood, right? We gave the hints, and actually the top is clearly the same imitation you have in the desk, and it's a complex texture which applies to hardwood. So, and the photo on the bottom was also in the lecture, so it was one of the samples we had of the pine trees, I think, right, with the conifers. We go to the a bit easier. This was kind of tricky one, right? And this is the point in which you have to read carefully. Because speaking about energy, but we're speaking about embodied energy, not the insulation of the building, right? And among all those options, we say that calcium silicate brick does not need to be baked, right? It uses only steam. And it was stressed and it was commented, right, in the lecture. So you need much less energy for this brick. It had other advantages, other pros, of course, but was the point. This was interesting also. Again, this is something we explain often, right? So the steel in compression reverse, right? We did in class, we commented in the activities, we had something, so I will not repeat, just it was explained. And you have here the 5, so the steel is actually 500 megapascal, right? But the point was the limitation to 400, right, in compression. And we said why. And then this was a bit tricky. This was not especially difficult, but this was tricky, right? So we commented that the timber, the humidity affects the actually cellulose, right? And it affects the strength. So the driest, the better. So it should be dry. The problem is it's very hard to have totally dry timber because the atmosphere, even in Sahara, there's some humidity, right? So we just use standard 12% as a nominal strength, but doesn't mean it is stronger. It is what we consider as acceptable. And finally, the 7 we saw before with the timber, this I just give up about north, south, east, west. Still, many people replied best glass wall for a working room for a workshop is southwest, which I do not wish you have as your office in the future, right? So, and that's it. About 10, 15 of the questions were extremely easy. Were done right by over 80% of the class. So the exam was okay, right? If you have more questions, you can always ask. And we have not much time left. So we're going to Windows. Windows are important part of the project, right? And many good architectures have memorable windows. This is one of my favorite. This is Voisey, one arts and crafts British architect who made fantastic houses. And those bow windows of one of his most famous houses is like really gorgeous, right? So there is a tendency of making windows the typical Annam-Dong villa 1 by 1 meter sliding window, which is okay, but windows are really one of the most interesting parts of design, right? Which can create not only the image of the building, but good interior spaces. So this is the plan for today and Tuesday. Let's go straight to the first part, Windows. And this example of a house in Kadoizawa, Hisao Koyama. Koyama is from the School of Luis Kahn, apart from being my professor, right? And his window shows this kind of obsession Luis Kahn and everybody behind him had on making a full world out of the windows, right? So you have the shades, the totally closed window, small part you put as a beer stand, right? Small openings for ventilation. Even you can open the floor and just clean and put the dirt on the ground, right? So there's a lot of things happening in just in a small opening of a window. Well, this is in Spain. This is one thing that fascinates me always, this kind of windows in the corner, especially these heavy stone buildings, right? So we will see just the basic requirements and then the basics of design. So I would say that windows in the first place are a design problem, right? So they really define much the image of the building. I brought 2 examples, one classical in Madrid, one modern here in Seoul. Not that they are good or bad, they just demonstrate that the window is what defines the personality of that facade. Then, of course, functionally, as it happens with the envelope in general, windows are like the key element which relate the view, the light, the ventilation, and safety, right? It's a weak point for safety, for privacy, but it's what relates the connection with the exterior. Again, this is another of my favorite buildings. This is Yoshita Niguchi in Tokyo. This is a visitor center. It's a little bit out of the center, but it's really fantastic, glass-only box, elegant and very well detailed. Then, of course, we have the climate control, especially air, sound, and heat. This is a window, I think, in the southwest Spain, in which the view is not important. It's just the light, diffuse light, and the air going through, right? So sometimes glass is not the essential part. But there is one thing that we have to consider. Some of those functions enter into conflict. And that's a problem when you have to comply with the codes and still you want to make a good architecture. For example, we need clean air to breathe. That's biological need. But letting the windows to have air inside makes us lose energy, right? And also, if we have air in, noise also comes in. So that point is very difficult to solve properly. So this is the summary of those basic three functions, I think. And the problem, the difficulty of Windows is that they are conflicting, right? So let's go again to the book. I think you have this in good quality in the final handout. This kind of nice summary of everything we can do with a window, right? So very clever, the shading outside. This is the only way to block really heat from the exterior, right? And in this case would be a rollable, so you can just change, and it can be even movable. Then you have, of course, the glass, right? And you may have inner shade. So let's get 3 layers, and the text just elaborates on those basic functions we commented before. Of course, you will notice that we have very difficult joints where the water can come in, and when we have thermal breaches, right? This is what we'll try to see a little bit in the following parts. So let's go about the functions. And I put cleaning because surprisingly, Korea is a country where cleaning windows is not a habit, but almost everywhere else in the world we have to have our glass clean, and that has some kind of safety issues. So I will just make a small annotation on that. So natural light, I will add some kind of the rules of the thumb, things that the old guys or what I learned in school in the 1980s, how we could dimension the windows just basically, right? So usually we made a ratio between the area of the room and the area of the window. There's not much science, just the practical experience about it. So usually we try to have at least 1/6 of the room area, right? Other codes give you more or less. So if you have a 10 square meters room, which is a typical bedroom for 2 people, we can have like a 1.3 by 1.3 window, which surprisingly is very close to the standard window you see everywhere, right? 1.2, 1.3 is that. So probably that comes from habit. For ventilation, again, this is mild climates, right? It's about a half the window, right? So in a room of 10 square meters, just would be half of that. And that ventilation, this is natural ventilation, is something that these tiny openings in curtain walls do not achieve, right? Because the ventilation area is very small, and that doesn't help cooling or renewing the air as we need. Again, this is traditional thing, right? Natural light, yeah, we usually say daylight. We don't call it the sunlight in general. Sunlight is like straight sun hitting somewhere, right? So daylight can be also diffuse indirect light or reflected light. So in general, in terms of volume, in bedrooms, we calculate 18 cubic meters per hour per person. In areas of stay, a bit less. When we sleep, we really consume a lot of oxygen. If we have a typical 2.5 high room, that means 7 square meters per person, and in living rooms, like 4 square meters per person, which again, if you see the standards for minimum space of rooms, they are defined like this, right? Like one single bedroom, 7 square meters is quite a standard. Double bedroom, 10 square meters. Living rooms for 4 people, 16 square meters. Many of the basics we have as a habit or developed in the 1950s, 60s, 70s come from these calculations. But the problem is how to put the air inside, right? Because of course, opening the windows is the easiest, but we will lose a lot of energy. So the most basic is by infiltration. So sashes are not perfect. You have slits, and the pressure of air just pushes inside. And if you have the typical building, usually you may leave the air go through the slits of the doors. You see the doors have slits, the air may go through, right? And this kind of air movement, right? If you have both facades, there's like a pressure and depression, and that helps to have the air moving. If you have a stack effect, that helps even more, right? This is very typical design choice. But the problem is if filtration is not controlled, and if you make the simulation, both heating and cooling are a disaster. So the tendency is, if you want to go simple, is just the aeration, I'm not sure how it is pronounced, devices. So in the sash or in the frame, you have small slits which let the air in, right? Sometimes they're automatic. So when the air is too dirty, it just opens and lets the air in. This comes mainly from Scandinavia, right? So Swedish, Danish, and those Finnish did this like a kind of habit. Now with the strict codes, we're importing them even to Spain, right? So that could solve that problem. But the best system is mechanical system, right? So you put clean air from the outside. You have very importantly a heat exchanger, a heat recover element. So when the air comes in, you collect the heat already, right? And then you just throw away the dirty air without losing much energy. That's the basic. So the heat exchanger is a very simple concept. There is a device with metallic sheets, very thin elements, which give a lot of surface of contact with the air coming in and going out. So they have like a surprisingly good performance. It's over 90% of the heat is recovered. What is the problem here? We need a machine, we depend on electricity. We switch off when the weather is nice, pumps and the fans are noisy. It's not always great, right? So this is the summary, right? And nowadays with the codes, every housing is mechanical. And some architects say that there's a good opportunity to have windows fixed, which are cheaper, easier to make. But I think as humans, we like to open the windows to have a clean air inside. So I would suggest to combine those things whenever it is possible. We are very short on time, but I invite you to think just for 3 minutes altogether about those three systems, right? Their advantages, their inconveniences. So you can say 4 to good and 1 to bad, and see in a table those 3 basic systems in one go. So you have some kind of a mental image, mental map to decide what to use and where. You can talk, you can discuss, you can fight. This is so fascinating thing about opinions. Okay, one more minute. Somebody already finished. Well, so you have your conclusion. You're undecided. Huh? Just guess yourself what is better or worse. Okay, let's continue. We have only one more activity to do. So cleaning glasses is something we do often, right? And most buildings are not safe outside. So I just annotated a few of the basic limitations. This is the Spanish code, right? It is very much similar in the rest of Europe. Of the limitations, such as you can clean safely from the inside. If you have to clean from the outside, you have to provide a safe system for the glasses to be cleaned, which is not hanging on ropes as it happens here. So this is the basic functionality of Windows, right? Now we go into the design. And the first is to have, this is mainly vocabulary, so I will not expand much. This is an image from the Desplazes book. The top, usually called a lintel, right? Actually, it's a structural element. The side, the book says reveal, which actually is correct. I see often also jamb, right? J-M-A-M-B. And very important, the seal. The seal is like the most critical part of the window because the rain, the water just accumulates here. It's like the weakest point by far. And then the spandrel, which is used also in Korea, right? Spandrel, which is the space. You have the section with windows and floors. By definition, it's the space between window and window in vertical. That's the definition of spandrel. So anything which is between windows is spandrel, whatever, right? About the parts. This is Michigan Apartments by Mies van der Rohe. They are still in use, you can rent them, but you cannot change anything. Yeah, it is very protected. So this is the original window by Mies. And that helps us to see many parts, right? So the glass or whatever we put is the sheet, can be glass, polycarbonate, can be paper, right? The fixed elements, right? And the ones which connect to the fabric is the window frame. The sash is the part of the window which can move. Finally, the hardware are the elements, the hinges, the handles, the locks. Of course, you have joints between sash and frame and between frame and building, right? And optionally a shade, which even in Michigan, the shade inside in summer doesn't work, right? July in Detroit, Detroit is terrible, suffocating. Going to typology, again, typology is mostly language. I don't think we need to repeat a lot. The book is the position. Actually, this is like an inside position. So this would be like the exterior. This is the interior, right? Usually you have the fabric protecting as much as possible the window. But for me, this is in the middle, not inside, right? But okay, that's the more inside you go into the wall, the more protected the window is, right? And on the exterior. Exterior is very popular choice because it is very, very soft, very continuous plan, but you have very weak points, right? In this case, the top point is the weakest part in terms of water leaks and also thermal performance. And then by functioning, by operation, the most simple is fixed, I usually put one F to demonstrate the glass is fixed, right? And then sliding vertical, this is how they're called in English, or sliding. Tilt and slide is one window which is totally locked, right? And you can tilt and then slide parallel to the other sheet. So usually one is fixed, the other moves just parallel to the other, what you can see here, right? So fixed is great in terms of the air leak. It's cheaper, right? The hung system works surprisingly well, but it is not very used nowadays because they're very complicated to make. They are quite complex. Sliding is very common, but it is by far the worst in terms of air leaks and sound, right? No matter how good it is, sliding windows have always a limitation there. And the tilt slide work better, but a bit more expensive to make. Casement are the ones just with a hinge, right? That is the most common window we know. Just a one notation on the symbology, because in the United States, right, and in Korea, the dots point to the hinge, right? In Europe, we do the opposite. So if you see in Europe one window with this thing, means the window opens with this axis. So be careful when you know about the origin of the maps, because that can be confusing, right? Tilt and swivel, it means it has two movements. Hopper opens to the outside with the horizontal axis, and awning, which is the most common you see everywhere in curtain walls here, is horizontal axis opening to the outside. And we have a jalousie, which is the series of windows which can open totally, that takes less space. They are terrible in terms of leaks and noise, so you use very seldom. And then central hinge are interesting because you can rotate totally, so they allow for the cleaning, right? And they close very well, but they're very complicated. They are usually very expensive. So when you see them, you can think they are really spending a lot of money. Accordion door is quite popular, but again, it's not a great choice. They are weak, they have many joints, and there are some makers who have very nice ones, right? But usually it's not a great choice if you need a good quality enclosure. And then by position, one window over one door is Tramson window. If it has kind of a polygonal shape, is called a bay window, which you can still see in Seoul in modern buildings, right? Clerestory window is a window which is higher. It comes from the churches, right? So, you know, the churches have like many levels. So the light would come from the tall windows, and the clerestory just gave name to those windows, right? And the Franklin Wright, for example, like to use those windows very often. So rooms would have light from at least 3 different sides with different qualities, which is interesting thing. This kind of summary with the basic notes I said before, right? Let's go into the material and modulation, the sizes and the materials. And this is kind of a summary. I will not explain in detail because you have the data there and you already studied the materials and their sizes. So that's done already, but that's the point to say. So depending the areas, right, the elements, we have many choices of material, right? So sash and frame is the basic election, but still the sheet, the joints, hardware, shading, you can have many choices. The most difficult and the most, let's say, critical is the sash, frame, and the sheet, because they define the image and also the performance, right, of the window. And then only speaking of the sash, of course, sash and frame, right? Sometimes we simplify, and they are both. I give also, we used to do this a kind of activity in class. I don't have time, so I give you just my opinion on that. We can have a timber is the most traditional material. Steel is not very used nowadays. Can have aluminum, PVC, combination of timber and metal, and even concrete, right? For sashes. And you have the general quality insulation, strength, maintenance, and interesting for us, customization. Usually timber, you can totally design. Of course, you can find the commercial sashes already designed, right? Steel, you can customize. The problem with the steel is the thermal performance, but there are makers who are working on that. and most aluminum and the PVC, you use custom materials, unless you are cheaper field and you make the building in Yongsan in which you create your own louvers, right, and so on. And there's some annotations, which I think is mostly the comments I said. I brought only one photo because this is in Nandaemun area. I think that building still exists. Steel frame were very popular until the 70s, until energy became an issue, because you need very little space, very strong, and you have a lot of transparency, right? And those last forever, right? And they are very versatile, but they have the problem with the insulation. In aluminum, I brought one example. This is a Japanese maker, right, Sankyo, which had a very ingenious solution. You know, the problem with the windows is that you design your beautiful window, right, with whichever partition, but then you put one operable sash, and then it becomes asymmetrical, becomes kind of messy, because the fixed part will have just the frame and the glass, and the sash will have a thicker part, right? And they devised a system in which all the elements have the same thickness. And to provide the mechanical strength and insulation, they have like a variable element of timber. So you can have a normal window or a big curtain wall with a lot of strength with the same element. This is one of the examples. This is to show you that you can design, you can make something different. So you have the timber to give not only the insulation, but also the strength. And you have one sash with a frame which fit in the 60 millimeters, which is the same you have in the fixed part. So all the facade, fixed or operable, we have the same thickness. About sizes. Okay, the size, as we saw before, speed of glass and so on, mechanical strength, right? If the window is fixed, the limit will be usually the glass. If it is operable, the casement window has to, it's actually a cantilever, right? It has to support its own weight without any other support. If it is a sliding door, you have to be able to move it, and it has the limit of the rollers and the strength of the support. Then you have the fabrication limits. As we said, glass and hardware have limitations. And finally, the handling, transportation, and use, right? If we go to the biggest glass, 3x6, to transport it is kind of a small nightmare, right? To the truck, to discharge it, and to store and to use it. So there's always limitations. Mechanical strength, usually the makers will give you some basic guidelines. They will check. If you are making high towers, high buildings, better check with engineers, because often this is, I think in Texas, some of the tornadoes in which towers would have lost in average 20% of their glass just because of the wind pressure. Then we have the fabrication limits. Often you make projects with classes of 10 meters of one piece. There's no maker who do it yet, right? And if you can make up to 6 meters, that's very limited use and it's very unrealistic. So just consider the usual things, right? Other thing is the sash size. This is like the general commercial, right? So most sliding windows usually have the hardware prepared for up to 2 meters by 2 meters, more or less, right? You can make bigger than that, but you will need special solution with testing in laboratory and checking if that works. And for hinged, it's a bit less, right? It's like 2.2 by 1.4. Again, you can have special solutions. You can make things bigger, but those sashes are enormously heavy, and that may maybe more weight than the frame itself can support, right? So if you go beyond the commercial sizes, you need an engineer to calculate and even some testing before building. This one example, this is one tower by one of my friends. This is TMP here in Myeongdong. It is finished recently. And they tried to put the largest glass they could buy in Korea. So a slat spring 4 by 2 more or less is the largest you can have as insulating glass in one tower. It looks like this is a nice building. Just as a curiosity, in the cladding is a black steel. This is a kind of a bath, chemical bath to make the steel black, 2 millimeters thick steel cladding. So weight handling, this is something we insisted on material. So glass is very heavy. So the 3x6 glass will be almost half a ton, right? Or over half a ton, which means really stress in transportation, handling, placement, but also the structure, the frame, and everything else. And the sliding door, the biggest door we said is already 150 kilograms in general. So moving that and the rolling elements will be really stressed. You need really good quality hardware there. And the important thing is the maintenance. So glasses sometimes break, right? Some of you noticed some broken glass in Hannah Square, which has been there forever. And since it was critical, may stand there for a few years, right? We had to replace several roof glasses already there. So that's something we have to consider, because sometimes we can only replace from the outside. And then the glass replacement can become very expensive. This is what we saw in class. And this is the Willis Faber building of Norman Foster. The glasses are placed from the outside. Actually, they had to replace glasses, and they said, oh, it is great. The wall stood, sorry, they didn't break, but you have to go from the outside, right? And this is single layer glass. And you see those two guys are really surely stronger than me, right? So imagine just a larger double layer or triple layer glass installation. That's really a physical work. Let's do the same part, which is the difficult part, the joints, right? Here, we have just 15 minutes left. Even if you don't finish, I want to see this with you slowly. This is something from the book. The book gives the example of the window mostly on the inside and gives a timber window. And this is very sophisticated. So this is probably the most complicated you can see. You have, as we said before, we try to have the fabric, the lintel, to protect as much as we can the frame of the window. So the water will slide, will not affect much. The horizontal section tells it. So we have the exterior part, right? Then the frame, which here is sophisticated, so we get 3 steps. Usually the frame, you can simplify as a kind of L-shaped element, right? Usually we will put one kind of Z element which collects the glass, and you get the shash. So this complicated thing can be simplified as this, right? You have contacts and you open to the inside. You notice that there is a gap between the wall and the frame. This is because construction is not exact. I insist, there is no millimeter in construction, and sometimes not even centimeters, right? It's like a full fingers or hands, or so you need to have some gap for adjusting the window, and then you need some elements to find not just the exact position by the millimeter, right? So there's one thing. The other thing is that this frame is fixed to the fabric, right? On one side or on the other, always in something which you don't see, right? So it is solid. And then the sash, again, I said it's basically one L or one Z shape. In this case, is a bit more format to have 2 more contacts. This multiplication of the contacts makes a better closing, right? So you have less air filtration and less sound. And this hole is interesting because if you have some infiltration, the air will decompress there. And if some water, which finally ends, it will slide down. So it's kind of extra safety. So this kind of gap, some people call it a decompression chamber or equalization chamber. You don't need to remember that, but it's just to additional safety to make this window airtight and also watertight. Then this is a cap. Usually you will nail to allow to replace the glass from the inside, right? So this is the most basic, and usually the frames are done in a way that they are the same section in vertical and in horizontal. Only the seal part is a bit more complicated. Other thing you have to see that the joints are always gaskets, usually neoprene, no silicone. Of course, the Korean 90% silicone, that's cheaper, but it's not better. Okay. And let me go back 1 second. To hide those joints, in this case, they put one element, but they don't explain what it is, but some render which hides those slits. And from the inside, you have an element also which is overlapping and is hiding that element. So this is overlap is a keyword I want you to remember, overlapping. There's the overlap of the fabric with the frame. You have overlaps of the sash with the frame. We have overlap of the cladding with the slits. This is the traditional way of doing, and this is what creates a good construction, right? Those elements give some flexibility, things can move, and still have that slit hidden. Nowadays, you see silicone everywhere. And okay, you can use silicone, but it's not a great solution, right? You overuse plastics and polymers, you pollute the air because they have gases which flow out, you make things dirty because they collect dirt, and over time they are not nice. So vertical section is identical, which is clever, right? So we don't need to explain, it's exactly the same happening. In this case, the cut is done cleverly, so if there's kind of any filtration by gravity, it will go out. That's very rare. See also one point in which, it's getting very fast. You have additional gasket to make sure the window closes well, right? So this window will not allow for any infiltration. So for ventilation, you would need to have those kind of aeration devices or some kind of mechanical ventilation, or open the window sometime. And there's the window sill. This is the most difficult part. Again, this is just an example of this window, but the principles are there. I outlined the basic elements because it was not very clear on a screen. And the sill is so complicated that in this case, they added some kind of aluminum part, right, to simplify the timber. To simplify, yeah, because in timber would have been more complicated, right? One thing they have is the frame. The frame is slightly different. So sill is always a kind of small pane. In the book, they connect to the sill. So if we see the window, that piece we have as a sill is this element, right? Which I don't think is a good idea, right, to fix, because this is a weak element, is movable. So in general, I think the bolt would go to the spandrel, to some solid part, right? This is the only thing I would disagree with the detail. The rest is quite reasonable. So you will see first the drip, always, right? The water as far as possible. You have a second drip in this element. You have a first decompression chamber with a weeping hole, right? So this will be like a 2. So you have weeping hole, decompression chamber. So anything which could leak goes out again, right? Third, we have the gasket with the final decompression chamber, right? So we have like a double safety here because it's more critical, right? So it's kind of everything done twice. Let me go back. I will clean it. Okay, so one is the drip, right? One is another drip. 2 would be this small chamber which decompresses and has a weeping hole. The third is the gasket, right? And then fourth is the second chamber. Many windows will have a small opening here, which will take the water out to the sill, right? You will see sometimes openings or small channels. They usually clog, they're not a good idea, but in this case, we do not expect the water to go so far. But sometimes you will see those openings, right? And then finally, we have number 5, the overlapping element to close the joint between the frame and the sill. And as much as possible, this sill would be one piece element, right? Not 2 pieces. So the water will not affect it. Everything else is more or less the same. Another thing which is interesting is this element under the glass. The glass needs also some kind of margin between the frame. Glass needs some kind of freedom of movement, so we always put some kind of support, right, of the glass. We never put the glass straight exactly in the size of the frame. So this is as complicated as it can be, right? Most frames you will see are much more simple, but you have the basic things we need to see. So if we go, for example, now to a PVC window, outside and inside, we recognize this, I will change to yellow, this Z element, right? With a dripper, the element to clip the glass, then the exterior part, which is an L, right? Actually, a Z because they have additional fixing point with only one decompression chamber. So here they just rely on a gasket, right? And you see the small channel here. So at points, they will have some kind of a weeping hole to get the water out. So this is simplified from the previous detail. And the complication inside is just because of the extrusion. The more layers you put, the more insulation you have, and the stronger the element is, and the lighter it is. And PVC, of course, needs some kind of a galvanized steel structure because PVC is very weak, so they need some kind of structure to support it. So if you understand that window on timber we saw before, this is easy to see, right? You just identify those basic elements and then you analyze how this is done. And of course, I would add the drip. It's not fancy, but that will help a lot. This is from one of the reference buildings, methods, very, very popular. You see we have the seal on one piece, right? The window frame and sash on line with the insulation. This is a very common thing. With one element will be fixed to probably the structural angle or the fabric, so you have very solid connection of that frame to the building, right? And everything else you can recognize the basic elements, right? This is kind of a T element with a cap under the glass inside. So you can just outline the basic elements out of the complication of that section. There's more examples. On the left, a bit more sophisticated PVC with the 2 chambers, right? Or a similar timber window with only 1 chamber, but with aluminum protection on the exterior, right? And you see now the standard is to have 3 layers of glass. And more examples. This is just to show you the intermediate element to make the thermal break, right? So timber will be insulated enough, but aluminum or other metals will need some kind of insulating material in between for them to reach the proper insulation. And then, okay, I was telling the plastic usually is a polyamide. Not all makers say what they use, but just this kind of engineering plastic. One more polymer we add to the repertoire. This is just for your information. It's just interesting collection by Detail magazine in which you see how the sachets have evoluted from 1950 to 2014 when this was published. So I miss the times where the windows were so simple, right? And now really are like a really monsters just to try to have this kind of insulation, right? But even with that complication, the basics with some detail exist there. Only we have more layering, more sophisticated insulation or mix of materials to have as insulation as we can, right? So this is again very much evaluated timber. What we saw probably is like stands like here, right? But if we want to go beyond the 1 or 0.6, we need really to have very specific solutions. So as we said before, this kind of zero energy building is quite difficult to achieve, right? And the same in aluminum. And sometimes you will need to have like additional insulation layer for it to work, right? To go to the standards of the passive house, which again is not easy. So but you have the full collection here, which I think interesting. And then another thing is the limitation of glass, right? EGU, you remember, DGU is double glass, triple glass. And with triple glass, we may have the insulation we need. With double glass, we are in the limit, right, on the required U. So we are really in the limit of materials in construction. And as we said, thin glass might help to this triple glass to be practical, because more glass is more embodied energy, is more weight, is less light we have. So there's many inconveniences there, and probably the thin glass will help. And I want to do this in class, but it's already the time, so we cannot do it actually. But we saw the most important, the most difficult part. The rest is just giving examples from the book, which we can see later. This actually you will do at home, right? You will put this as part. I forgot to put the assignment for next week. So we have the plinth detail plus the seal, right? So for Friday next week, which is the 18th, you just copy the detail of the plinth and the detail of the seal here, right? And that's assignment 7. Those who are doing their project do not need to do this, but still, I think it is good you draw it and you understand it perfectly, because that's how we understand windows and how they are made. So far, 2 students are going to do their project. Anybody else is planning to do the project instead of the other things? Okay, so we didn't have time to explain the first part. Did you submit today the project? Please email me and I will upload at least the guideline for the thing. So if you don't have it on Friday, it can be later, but the time is very limited, right? So those doing the project, we have a bit more time, but we need the project first, okay? So the handout will be soon. So then it's just examples, many examples using the review session. So as we said, on Monday, we'll see the curtain walls. This is the references we have here. You have any question, write it. And remember, on Tuesday, we have a quiz. The same, timber sustainability, plastics, waterproofing, envelope basics, right? And on Friday, the assignment 7.1, which is plinth, 7.2, which is seal, or alt assignment, which you may expand a bit more, but I need immediately as soon as possible your project. So I can give you some additional guideline. Okay. So that's enough for today. See you Tuesday and have a happy Pepero Day and a nice weekend. Yes. How was the empty? Sorry, the
The trip you went to with the studio